This next session is on the frontiers of the second law, and our first speaker is Adrian Bejan from Duke University.
Thank you very much. My contribution to this discussion is really I'm making an effort to bring to your attention some work that has been occurring beyond the frontier, that is, in addition to the accepted laws of thermodynamics. And to make that step clear, I begin with a review of the laws that we use. For example, in this case of a drawing out of Professor Keenan's 1940s book, two statements are made: energy conservation. The second one is a statement of a tendency in time, one way or irreversibility. There are other statements that are derived from these first two. But the major observation is that thermodynamics, as we practice it, is a science, or a science of systems as black boxes without configuration. Nature is quite different. It is in fact permeated throughout at all scales by configuration. So there is a phenomenon of physics of generation of configuration, one that is not covered by a law, and for that purpose I proposed the law that's listed at the bottom, the constructor law. You can read it. It is a statement of evolution of configuration in time. It is a statement that recognizes a tendency in time, or a time arrow, and it is an animated movie of everything that flows and does it with configuration. I will show you three examples of how this statement covers the entire spectrum of configurations in physics, from the animate to the inanimate, all the way to us, the societal. The example of inanimate flow structure is the tree-shaped flow in all the river basins on Earth. If you invoke the idea that I stated, you end up discovering that the best way to flow as rainwater out of an area to one point is by choosing drawings of this type, which are drawings in which each mother channel is attached to four daughter channels. And at the bottom, you see the great coincidence that this prediction really agrees with the well-established scaling laws of all river basins, laws that have been known since the 1930s. The equivalent, really, example from biological systems, they go under the name of allometric laws. One example from our work is the prediction of all animal locomotion from the principle, the conclusion that the larger animals must travel faster, must wave their bodies less frequently, and must be stronger, not qualitatively, but quantitatively precisely in the way that these formulas indicate. The bigger conclusion is that all animal locomotion is deterministic, it is predictable, and also that flying is really the same as running and the same as swimming, as fighting intermittently against two evils, gravity and horizontal drag. And finally, my third example is the movement of our own mass. This is the engineering, or the human and machine species evolving in our times. If we maximize access in the flow from one area to one point, we discover things such as, the optimal shape of the rectangular territory, and coincidentally, we discovered why the shape of Atlanta Airport should be the one sketched there. And at the larger and more complex scales, we find why human settlements should be distributed in multi-scale fashion all over the globe. Very few large cities, many more small cities, and why the distribution of such settlements must be linear in a log-log plot. In other words, from principle, we predict all the Zipfian distributions of such multi-scale parameters. And my concluding view graph is shown here. It is my conclusion that with the constructor law, our thermodynamics becomes a science of systems with configuration, or read in the opposite direction, our design ceases to be art, it becomes closer to being science, an activity, obviously a mental activity that's with its feet planted firmly in principle. The statement itself is a statement of tendency in time or evolution in time. Flow systems or flow drawings are replaced by easier flowing drawings in time. There is no maximum nor minimum, not a minimum mentioned in the statement, and there is certainly no end to this evolution. It's just the direction in which the screens of this animated movie replace one another. One such movie for every known flow system, animate or inanimate. And the literature that I'm bringing to your attention is full of work done by us, but especially now by others, on how to predict not only what I alluded to, but all the results made by others in the past, others who have chosen to state or postulate ad hoc minimization of this or maximization of that principles in the past. Thank you very much.
Thank you very much. Our next panelist is Bjarne Andersen from the Niels Bohr Institute in Copenhagen. Oops. Okay.
Thank you very much. There have been many fights about the second law of thermodynamics and about definitions of entropy. Really, it's very much like people in New Zealand told me that there are many ways of slicing a kiwi. So it's still my belief that entropy survives as a concept and that it applies equally in chemistry, in quantum computers, to black holes, to everything. We heard this quote from Albert Einstein also earlier today, that classical thermodynamics is the only physical theory of universal content that, within the framework of applicability, of its basic concepts, will never be overthrown. That's quite a statement. I don't see any sign of contradiction so far. Having just been at a meeting on cooling of atoms and molecules about a month ago, I felt compelled to write the last statement here, that the cooling of atomic systems is not really the question of removing its energy, but removing the last bit of entropy from these systems. So you can extract the energy, the temperature getting close and close to that absolute zero is really a matter of removing the entropy. Now, that is done on the average. We have an increase of entropy, not of an individual particles, but on average. This is a plot that I took from work by an Australian group a few years ago. The probability of certain changes of entropy of that tiny nano-size system, and most of the bulk of that distribution is in the area of entropy generation. But there is a little tail, the one that I've marked in red, which actually showed that a few systems decreased their entropy during this process, which was repeated over and over again. And now that is not a violation of the second law of thermodynamics. You cannot drive your household on that, because more often than not, you're going to lose. So let's keep in mind that just a single atomic system violating the second law of thermodynamics is not a violation of the principle, because it's the rare occasion. Now, when you want to check the second law of thermodynamics, you can make good use of some of the ideas that we put forward in finite time thermodynamics in the path we developed there. One of the important lessons you learn is that you have to make sure that you specify precisely what it is you want to optimize. Is it the efficiency? Is it the power of the system? they all require different modes of operation. Also, the newer concept of thermodynamic geometry, which is listed on the right-hand side of this view graph, shows that the bounds that we have there for the entropy change in there for the loss of availability look very much the same, but they are a little different. So you have to make up your mind what it is you want to maximize. Otherwise, you're getting into these eternal fights about my system is better than your system. The next general statement is that in order to achieve any optimum, you need to have controls. Nothing happens by itself. It's the operator, not nature, that decides what's the right way. So all optimizations, I can't read, sorry. It requires controls to steer the process in the desired direction. That could be controls on reservoir temperatures, conductances for such a piston system. Again, I'll remind you that the path will be different, whether you do it by, if you want to maximize power, that's a control, optimal controls, or if you want to maximize the efficiency of your system, then those are the controls. Similarly, one can optimize the behavior of distillation columns. Instead of just heating at the bottom, cooling at the top, you can gradually heat or cool to increase the thermal efficiency, and you can again use optimal sequences for something as abstract as simulated annealing. And finally, you need to be very careful about how you define your system. In this system consisting of a hot reservoir with a flow-through heat exchanger, leaving it at a somewhat lower temperature, in the cold reservoir, you want to extract energy, work here, whether you define your system with this dotted line or with that dotted line. That is, whether you include the sort of waste reservoir T2 in your system or not will give vastly different results, as will whether you have heat transfer with the normal Newtonian transfer, you have thermodynamic transfer, or with the red one, you have radiation transfer. And finally, you get different results whether you work with the Bose gas or with the Fermi gas. Not, of course, with efficiency, you can never get better than the Carnot, but how much power you get out per stroke. So the bottom line is be very, very careful about everything about the system. You have to define it beforehand, otherwise you're going to get into a fight with your neighbors. Thank you.
Thank you. Our next speaker is Miguel Rubi from University of Barcelona.
Yeah, thank you very much. First of all, I would like to thank the organizers for inviting me to participate in this very interesting panel discussing the frontiers of the second law. Well, what I'm going to do precisely is to discuss about one of these limits of the application of the second law. And I'm going to discuss how to use the second law to extract information about the evolution of the small systems. So small systems are systems constituted by perhaps many, many particles, but not for an infinite number of particles. So these systems exhibit two main characteristics. The first of them is that they don't satisfy the thermodynamic limit. So you cannot make that the number of particles goes to infinity because the system contains a finite number of particles on one hand. And on the other hand, what is important is that these systems are very sensitive to the existence of fluctuations. They are embedded in a heat bath. The bath contains fluctuations, and these perturbations affects very much the dynamics of these systems. Okay, now what I'm going to say is the following thing that, well, no, I'm going to discuss the previous one. In respect to examples, so there is plenty of room in the middle of a macroscopic description you perform by using thermodynamics or non-equilibrium thermodynamics, describing the system in terms of a few number of variables, for example, the energy, the volume, or the mass, and an atomistic description and a microscopic description proposed by statistical physics, which describes the systems in terms of the positions and the momenta of all the particles and perhaps of all the degrees of freedom. So there are many systems which pertains to this domain, which we have called the mesoscopic domain, just in the middle. For example, clusters you can observe in nucleation processes, biological cells which interchange mass and energy with the environment, and single molecules you can deform upon application of an external force. Well, what I'm going to show is that, well, to these systems you can use the second law, and we have proposed in the last year a theory, we call it mesoscopic thermodynamics, mesoscopic non-equilibrium thermodynamics, which applies the method of non-equilibrium thermodynamics to these scales. Okay, now. Well, so let me give you an example, a brief example. The example is the case of a single molecules I deform upon application of an external force. So you have two types of variables here. So the first one is the position of the center of mass, indicated by x, which is a slow variable. And the other one is capital theta, which could be the size of the molecule or the angle of the molecule. And, well, a non-equilibrium thermodynamic description, what it does is to propose this local equilibrium hypothesis to establish this Gibbs equation, in which the F is present. You have to add the work done by the external force. But now these quantities are average quantities. So this capital theta is the average value of the size, for example, of the particles. So if you go to a shorter time scales, you must consider the fluctuations. You must consider that the actual value of this capital theta is not equal to the average values. There are some deviations, and these deviations are contained in this probability distribution function, which depends on the x variable and theta variable. Okay, now what we have done is to propose an extension of the concept of local equilibrium to the meso scale. So proposing this Gibbs equation, which contains a chemical potential defined in the phase space, in the space spanned by the values of x and theta. And now what plays a role is the probability distribution function instead of the density distribution function. So this is the Gibbs equation, for which you can apply non-equilibrium thermodynamics and obtain the evolution equation for the probability distribution function. From it, you can calculate the moments, and from the moments, you can compare with the experiment, because the moments of the probability distribution function are related to physical quantities. So now, proceeding in this way, we were able to show that one of the famous equations or important equations of the theory of stochastic processes, which is the Fokker-Planck equations, can be derived, can be obtained by using this theory. So it has thermodynamics grounds. So this is the Fokker-Planck equation. So just establishes a link, a bridge between thermodynamics and stochasticity. So, well, we have applied this theory to several systems, for example, to chemical reactions, to translocation of ions, and in this case, we have obtained nonlinear laws related to the reaction rates and the forces and the thermodynamics forces. For example, the Arrhenius law, the Butler-Borman equation, or the law of mass action can be obtained using this theory. Well, now, second example I would like to discuss very, very briefly is the case of the RNA unfolding on the tension. What you do is to take a molecule of RNA, apply an external force, and then this external force so deforms the molecule and is able to break the bonds. These bonds here are broken as a consequence of the force. Right? Now, what we have done is to show that this probability distribution function of finding a molecule with n base pairs broken is given by this expression. Jn is the unfolding rate, the rate at which the molecule unfolds, and this equation together with an expression of the unfolding rate give rise to the master equation. So we have shown that the master equation governing the dynamics of the system can be obtained from this mesoscopic non-equilibrium thermodynamics. And the last example, very quickly, is the case of the muscle contractions. You see here in this picture that this myosin head moves along this actin filament, and then this process can also be obtained, can also be explained by using the mesoscopic non-equilibrium thermodynamic theory. That's all. Thank you.
Thank you very much. Our next speaker is Sinje Kjelstrup from the Norwegian Institute of Science and Technology.
Thank you very much for letting me in on this panel. Dear audience, classical non-equilibrium thermodynamics uses Gibbs equation and the conservation equations to define the fluxes and the driving forces in agreement with the second law. The problem is that the standard variable set does not describe activated processes. They are non-linear, as explained right now by Ruby. I will follow up on his examples because we think that mesoscopic non-equilibrium thermodynamics can mend that problem, long-standing problem in classical non-equilibrium thermodynamics. The example I will take is active transport of calcium by the hydrolysis reaction of adenosine triphosphate. So this is a case where chemical energy is used to transport ions against the chemical potential, active transport. So how do we do it when we introduce this mesoscopic level? We need a new variable that is not controlled from the outside. And when you deal with a chemical reaction, the logical variable is the degree of reaction. So you have sequence of enzyme states. Here you see the calcium ATPase, and the coordinate runs from the start of the reaction to the end of the reaction, and this coordinate will then replace in normal biology what they call, oh, this is not the the enzyme cycle. So it is a theory that will be an alternative to reaction kinetics. Yes. So the statistical basis was given this morning also. It is the Gibbs entropy postulate that we use, and it was just described by Miguel Ruby. On the basis of that, we define the chemical potential, or here, the Gibbs energy of the reacting mixture, and we define it in gamma space, saying that at each state we are allowed to use Gibbs equation and also all the ordinary chemical potentials. It means that the reaction energy, Gibbs energy, will be described by this probability function. I called it F, Miguel called it P, plus the activation energy barrier that you see to the right. So then, once you have made these choices, everything becomes exactly as in standard non-equilibrium thermodynamics. So we, again, derive the entropy production from the conservation equations, from mass and energy, or whatever you want to include, momentum, and Gibbs equation. And you see the familiar bilinear form of the entropy production. And in this particular case, you have a contribution from the reaction, the first contribution here to the right, and from the calcium that is transported uphill against the chemical potential. And then, because of the energy equation, we also have energy, heat flow. And we all know that biological systems have heat flow. And that is, as of yet, not included in the description of enzyme kinetics. It should be there to quantify the lost work in these important systems. So now we write the theory on the mesoscopic level, but we need to connect with experiments, so then we have to integrate over the internal variable space, and what comes out is the nonlinear type of equations that you observe for the chemical reaction. You see that in the upper corner here for the chemical reaction. This can also be derived in other ways. And you have coupling to the other forces, to the osmotic force, you could call it, and to the thermal force. And the Onsager relations apply on the mesoscopic level now, so the matrix on the integrated level is no longer symmetric, but there are relations between the coefficients because of the Onsager relations. And we see, because of the coupling, that heat, total heat, can be transported also in isothermal processes. Of course, reversible heat transport can occur in these systems as well. So, this gives some perspectives, some conclusions, that by doing it in this manner, we keep the structure from classical non-equilibrium thermodynamics, and we are able to then give rate equations as thermodynamic basis. We can use the theory on very small systems, like Miguel already has described, and I think in this particular case I demonstrated it, the principles only, for active transport. We give a thermodynamic basis that contains more information. For instance, it's possible to see that this ion pump is indeed also, it's not only an ion pump, it's a heat pump. So, that concludes. Thank you.
Thank you very much. Our next panelist is David Jarl from Bellater in Catalonia.
I thank the organizers for the opportunity of participating in this discussion. Here, one of the frontiers of current technology is the design and manufacturing of small devices working at high frequency. In this situation, the classical transport equations, as for instance Fourier's equation, is no longer valid, and more general transport equations incorporating memory and non-local effects are necessary. Here I have shown in the first line the so-called Guyer-Krumshall equation, which incorporates memory terms in this rate, in this time derivative of the heat flux, with tau being the relaxation time of the heat flux, and the last term is a non-local term with L is the proportional to the mean free path. This equation, these non-local and these memory terms are interesting because they say, for instance, that the propagation velocity of heat pulses will not be infinite but will be finite, and that for very small, very thin nanowires, the effective thermal conductivity will not be the usual bulk conductivity, but it will be smaller. Therefore, this equation is useful on practical grounds, but it has the problem that it is not compatible with the local equilibrium, formulation of the second law. For instance, you see in this non-monotonic curve, which represents the entropy of an isolated system as a function of time. This describes the behavior of the total local equilibrium entropy of the system, of the isolated system, if you impose on it an initial sinusoidal temperature profile, and you allow that this temperature profile decays according to this more general transport equation for the heat flux. However, if one modifies the entropy and the entropy flux in a convenient way, you obtain the second curve, which exhibits a monotonic behavior. Therefore, it is interesting having this more general entropy because it provides a way of defining a second law for these generalized transport equations incorporating memory and non-local effects. In this entropy and in this entropy flux, you will see that the non-equilibrium contributions are perfectly identified. They depend on the relaxation time tau, which is connected with the memory term in the equation, and the entropy flux is connected with the non-local effects. This is only a very simple example of generalized transport equations, which could be generalized to higher order fluxes and gives some equations, some transport equations, which are able to describe the transition from the diffusive to the ballistic regime, which is also one of the frontiers of non-equilibrium of transport theory. I will not deal with the details, but you see the points, you will see in the figure that the points for the effective thermal conductivity are much smaller than the usual Bull conductivity, which will be the asymptotic value. And here we represent the effective thermal conductivity in terms of the size of the system as compared with the mean free path. An important question arising in non-equilibrium thermodynamics is not only entropy but also temperature. Here I have presented a non-equilibrium entropy in an explicit way, but if we differentiate this entropy with respect to internal energy, we will obtain a quantity which could be identified as a kind of non-equilibrium thermodynamic temperature. But therefore, the problem arises of which is the physical meaning of this temperature. This physical meaning may be meaningful, for instance, in non-equilibrium steady states. If you are very far from equilibrium, situations are much more problematic. Then the definition of this thermodynamic temperature does not solve at all the problem, the very complicated problem of temperature in non-equilibrium states. In non-equilibrium states, there are many different temperatures. You may generalize, you may extrapolate many expressions, many equilibrium expressions which contain temperature in equilibrium, and you may use them by extrapolation to define effective temperatures out of equilibrium. We think that the problem of temperature out of equilibrium is to be able to identify which is the physical meaning of each of these temperatures, which have an operational meaning, and to be able to relate one of these temperatures to the other temperatures. For instance, in this system, this non-equilibrium temperature defined as in relation with the derivative of the entropy with respect to the internal energy was seen to be the kinetic energy of the degrees of the translational kinetic energy of the degrees of freedom perpendicular to the heat flux. But this temperature is different from the average kinetic energy along the heat flux. In other situations, one may explore different non-equilibrium temperatures, or for instance, in systems with viscous shear pressure, where you will have kinetic temperatures, we will have configurational temperatures, and also fluctuation dissipation temperatures and other kinds of temperatures which will be different. In the situations we have explored, the non-equilibrium temperature was the minimum of the different non-equilibrium effective temperatures which were defined in the systems. Therefore, here I have presented a simple model which is valid for a modest range of equations, but which validity may be enlarged to a wider range of equations, in which you have explicitly a non-equilibrium entropy, a non-equilibrium entropy flux, and a diversity of non-equilibrium temperatures which may be related to each other. Thank you very much.
Okay, thank you very much. Our next speaker is Miroslav Grmela from the École Polytechnique de Montréal.
I would like to thank the organizers for giving the opportunity to be here. So what I want to do is to make two comments about the entropy. One about the origin, and the other one about the mathematical environment in which it comfortably can live in. So about the origin. So one possible way to approach this problem is to begin by recognizing the fact that there are, for example, that hydrodynamics is a very successful, provides a very successful setting for some systems in some situations. Yes, recall the history. There is Euler 1770 or something like that. No, just the framework to explain some experience coming from some type of measurements. No particles, nothing involved. There are many examples like that. So now, seeing this fact, empirical fact, from the microscopic point of view, it means some emergence of some pattern in solutions. Yes, and this emergence of pattern is, if seen as a time evolution process, is associated with some kind of Lyapunov-like functions, and that's the origin of entropy-like functions and entropies. So look, from this point of view, so I am using the pattern recognition rather than, say, ergodicity of coarse graining, because of to evoke our intuitive understanding of the complexity of pattern recognition. For example, try to identify what kind of coarse graining you are using by recognizing now my face. Yes, so so any time where one goes from details to some kind of pattern, I would suggest there is an entropy involved, and by providing some kind of the dissipation, that's the putting in some pattern recognition process. For example, in the Boltzmann equation, by adding the collision term, it is the way, by following the time, one gets to local Maxwellian, which is the pattern in one particle distribution function of equilibrium state. I suggest that similarly, possibly in this thermodynamic quantum theory, by adding to the larger theory the dissipation, one provides a setting for recognizing a pattern, which is the usual quantum mechanics. Okay, so now let's go to this mathematical formulation. The setting is contact geometry. Now, one can get into this conclusion by following the equilibrium thermodynamics as well as non-equilibrium, and just by using some mathematical argument. So let's go to equilibrium. So it's basically Gibbs. Yes, in fact, Gibbs when he published 1870, I don't know, 3 or something like that, there were 3 papers in which he formulated thermodynamics. In all titles of all 3 papers, there is geometry somehow. He really was aware of the importance of geometry. Yes, so and in fact he used this what is called Gibbs manifold. By it is one can go as follows. The transformations of importance are, well, thermodynamics, in fact, is a maximization of entropy subjected to constraint. These are Legendre transformations. The next question is, what is the space in which Legendre transformations act naturally? So something has to be preserved, and it is a one form which in fact has a physical interpretation of a first law. Yes, and that's the setting of contact geometry. Now, the interest, well, we go from the to 5-dimensional, from 3-dimensional space, yes, of number of moles, energy, and entropy. We just extend it to the 5-dimensional space by including also temperature and chemical potential, and that's the way to go to the contact geometry. And this kind of extension is also, in fact, when we follow the classical non-equilibrium thermodynamics, it started with hydrodynamic equations. That's this first line. And the first step is to lift it to higher dimensional space by considering also evolution of the local entropy. And if we add also the time evolution equation of the conjugate variables like temperature and chemical potential, we get to the setting. And what is interesting is that the time evolution, which is also dissipative, is in fact appears as a sequence of Legendre transformations. Now, this it's quite general. It is true for the Boltzmann equation, and it in fact can be it's very useful as some kind of structure setting to construct for example, extended hydrodynamics of complex fluids. As an example, there is
please wrap up.
Suspensions of nanometric particles, yes, and so on. Okay, and also there are some mathematical arguments which also lead to contact geometry. Thank you very much.
Thank you. Our next speaker is Lindsay Gordon from Wellington, New Zealand.
My colleague, Clark Maxwell, couldn't be here today, but my work is on Maxwellian valves, and otherwise known as the demons. And I see two ways of constructing these valves. The first, as you can see there, are coupling of varying processes within the system. The other is in the processes which has, as one process in the mechanism, one non-reversible process. We all know about osmosis, but the osmophoresis is probably not so well known, where you have the membrane changing or moving under the movement of solvent through the membrane, and being a closed compartment, the membrane moves accordingly. Now, if we take the osmophoretic engine, which has the one molecule of solvent and a membrane now made up of a solid porous piston enclosing a liquid membrane, which can, through which the solute and the solvent can both pass, we'll notice that the solvent is passing through to the solution side until such times as the solute passes through the membrane. Right? All these processes are by diffusion. And then the solute, having passed through, the solvent then changes direction and moves through in the opposite direction. So this osmophoretic engine, unlike the Szilard one, which needed partitions put in, the demon to look for the molecule, the coupling devices having to be done, all the demon's work here is not here at all, you notice. And this is fluctuating completely forever. And what about the membrane? Well, it's composed from time to time of those three particular phases, as you see there. To look at this, just a little bit of the membrane itself. That triangle represents all the compositions that the membrane can have. The top quadrilateral is purely the membrane liquid. The little red square, that is the composition when the solute is passing through. The blue square is when the solvent is passing through. And you notice that there are only the three phases, and the double-headed arrows give you the fluctuations between all three possibilities. Now, having got our engine that fluctuates without any information, without any demon to look into it, what are the other things at the end there about information theorists like to put into these systems? We don't need any of those. This thing goes by itself. And we look at the little piston. It's tied up with a yellow plate there that pushes the plates attached to a belt. And it pushes at the present time because the piston moves away from the solute molecule. And when the solute molecule goes to the other side of the membrane, this yellow plate then slides down frictionlessly to the lower belt and pulls. And it's continuously moving around in that particular cycle of events, and the weight is always lifted. You'll notice that we have here a problem. When the solute goes through the membrane, there's no osmotic pressure to drive the solvent through the membrane. Now, under normal circumstances, that would mean the weight could then fall back because there's no osmotic drive to the system. But this is the trick in the system, because when the solute is in there, the solvent is unable to be in there because it's only a three-component system and it's only got three phases that it can go through. And besides that, so when the solute is in the membrane and there's no drive, it's not only stationary, but it's blocked the system. So the weight cannot fall back. And this is the problem that Feynman had. So this weight will continually, and what is giving this possibility of lifting the weight? Well, the osmophoretic engine is sitting in a one-temperature bath, and the heat, of course, being put into the work, the temperature is lowered. Now, I want to go to another system. I said on, and anyone looking at this will see that on the left, you have a simple pore in a membrane that allows solute to go through the membrane where it would not have been able to go before. There's an enzyme system in red, and it allows the solute to pass. Now, if it's a simple system like that, we're going to get an equilibrium at some stage with the concentrations or the chemical potentials of the solute S in left and right-hand side. No problem. I've worked with these systems in the 60s. I know them well. The right-hand side is exactly the same except for one thing. The left-hand entrance and the right-hand entrance to the enzyme are at different distances from the axis of the enzyme. Now, if we allow that enzyme to undergo Brownian rotational motion, then we'll find that the potential energy of the solute in transfer through that membrane will be picked up by the solute, and movement will be from right to left more than left to right. There is still some movement from right to left.
Please wrap up.
Left, right. So we have the equation at the bottom there, which represents what we might call a steady state rather than equilibrium, where the left-hand side is of higher concentration than the right-hand side by the exponential product that we see there. That's my time.
Thank you very much. Next, we'll hear from Eric Schneider from the Hawkwood Institute.
Good afternoon. I'm going to change the tenor of this conference quite quickly, moving from quantum systems to biological systems to global ecosystems. I'm an ecologist. One of the first things I started to look into in ecology of what were the laws of ecology, where were the F equal MAs, the Navier-Stokes equations, where could I turn? One of the first volumes I looked at was Schrodinger's book, What is Life? In that, he pointed out two aspects of living systems, the order from order, where he pronounced ahead of Watson and Crick, the DNA and RNA. And secondly, he talked about order from disorder, interjecting thermodynamics into biology. To learn my thermodynamics, believe it or not, I first turned to Hatzopoulos and Keenan. I had an association with Waterloo University at the time. Here I'm showing you three different types of non-equilibrium systems. The first, the Bernard system, which is well known to all, which is driven by temperature gradient. The Taylor system on the bottom, which is less known to people, which is a pressure gradient system, which puts highly organized microscopic products in the annulus between the two rotating disks. And finally, the Zhabotinsky reaction, to which I don't have to say much because of the work of Prigogine and Niklaus. Looking at another gradient system is the one we've seen earlier today between the sun and Earth in space, a gigantic gradient if there was ever one. The ecosystems of the Earth are run by this gradient, first from the sun through primary producers to secondary producers to the higher organisms. In ecosystems, we can study the flow of energy by looking not only at weighted flows, but flows throughout the systems. In doing so, we can determine the energy throughput through the systems, the cycles in the systems, the hierarchies in the system, and the heat and entropy production in the systems, from which we see in ecological successions, directional processes that directly tie them to Darwinian evolution. The second approach I took was to look at a dissipative system, in this case a tree. Here we have 800 watts per square meter coming into the tree, 100 kilograms of water per day coming out an average 25-meter tree. The thing of interest to most of you is, one, it's a dissipative system, bringing a high-quality energy from sunlight, and most of the energy going out is latent heat and evapotranspiration. Only 1% of the energy coming into the tree is turned into leaf and bark. The rest is reflection, heat, but again, it's bringing in high-quality energy and putting out evapotranspiration. Can we see this on a global scale? Here's a satellite map taken by one of our satellites showing temperature cold in blue and red in being hot. Forget the oceans for the time being. We can see the El Nino on the far left-hand side of the Pacific Ocean. But what the most major thing that we see is the cooling over our forests, the Amazon, the Congo, and the Indonesian forest. This is just like our tree showed us before. Most of the energy is turned into latent low-grade energy. Issues for thermodynamics. The first one I ask of you is to resolve the conflicts between information theory and thermodynamics. We all know the story of Shannon and von Neumann and the mixture that was showed immediately that the two equations are very similar, but one dealing with probabilities of an event taking place and the other taking place of probability of entropy production in the systems. The next thing, maximum entropy production. Confirm it or properly kill it. A book came out last year, Non-Equilibrium Thermodynamics and Entropy Production. It got itself a centerfold in Nature, order out of chaos. These boys are getting a lot of work out of this. They're wrong. Phenomenologically, through all our systems, as Professor Bejan has shown in engineering systems and I've shown in biological systems, that there's a minimization rather than a maximization issue that's taking place. And finally, because some of us go between science and policy, I think one thing, advice I might give us all, and it's done in green, I'm sorry you can't read it better, but encourage policymakers to use exergy analysis for future energy development projects. An example of this is the ethanol craze is presently going on in the United States. It's an exergy negative process. The same thing with coal to fuel oil that my governor in Montana is trying to show. I hope just with asking these questions, I might show you some of the issues that those of us standing outside of thermodynamics see as we look to the inside. Thank you very much.
Our final panelist needs no introduction.
Well, since we have to meet deadlines, I'm going to be brief. I just want to point out that there has been a lot of discussion about trying to explain why entropy increases and how it increases and what's the equation of motion and why some equations of motion are reversible and some are not, and what is right. I just want to point out that as far as I know in thermodynamics, there is no statement that says the second law implies the increase of entropy. The second law only says that the entropy cannot decrease, but there's nothing wrong with the entropy staying put. Now, there's no question that we have evidence that in some cases, there's a lot of evidence that it appears that the entropy increases, but that's not the second law. The second law says that entropy cannot decrease. And we have to think about it, because maybe the reason we observe some entropy increases, there's interactions between the environment, not energy interactions, but an entropy interactions. I'm not suggesting to propose that. I'm saying that that's one of the most unlikely possibilities. But anyway, the point is that we don't have to state that if you have an equation of change, it has to, by the second law, it has to show an increase of entropy. It has to show not a decrease of entropy. A decrease of entropy will violate it. That's all.
Wow, that was great. Okay. Can you stand up to the microphone so we can hear what you say? That would be great. He still has 2 minutes and 20 seconds, so...
In fact, I would like to express exactly what George said in a different way. If you approach the definition of entropy the way Professor Kinner would ask us to do, you conclude the following. If a process is reversible, the entropy remains constant. If a process is irreversible, the entropy increases. That if is of great value, and proof of that is that we started with engines some 350 years ago with an efficiency less than a fraction of 0.1%. And today we have achieved in combined cycles and of gas turbines thermodynamic efficiencies that exceed 90%, which means that thermodynamics did not impose from the beginning that our processes be irreversible. It simply predicts what the consequences of irreversibility are. Thank you very much.
Great. Thank you very much, Elias. Okay, So we now have thanks to George putting us back on schedule with a stirring address, we now have time for 20 minutes of questions and discussion. Please.
I'm Gianpaolo Beretta. I like what George said, but I want to say this fine point, which has to do, of course, with the quantum theory. If you take unitary evolution and you take the equilibrium states according to unitary evolutions, then for a given value of the energy, you find many states that, according to that dynamics, are stable equilibrium. If you want to make it in such a way that for a given value of the energy, only one of these states is stable equilibrium, and stable, I mean, according to dynamical theory, the Lyapunov stability, then you do need to have irreversibility in your equation of motion if you want to derive the uniqueness of the stable equilibrium state for the given value of the energy. So that was my addition to your statement.
Well, I think it's a good point that we should discuss further.
Very keen and ask. Okay.
My name is Sam Miller, and as we all know, thermodynamics deals with real physical systems. Real physical systems typically involve boundary conditions, such as most gaseous systems are bounded by some sort of cavity wall, a real physical interface. My understanding of the H theorem is that it's derived by making certain fundamental assumptions regarding those boundary conditions. You have to include the boundary conditions in the derivation with that. So the question is, what is the physical basis for those assumptions for real physical systems that then lead to the H theorem?
Anybody want to comment here? Yes.
Yeah, I just I believe that boundary conditions should be seen some other physics, which is not in the bulk, but some other physics is taking place on the boundaries. Yes, and this together, but usually this physics which takes place on the boundaries is some kind of on different level than I would just remind you the interesting history of just boundary conditions in fluid mechanics, just the non-slip boundary conditions. It has a long history and has no microscopic explanation, real explanation for the time being. As for the H theorem, then indeed one can, there are proofs that if with some kind of artificial boundary conditions, one can disprove the H theorem for the Boltzmann equation. Yes.
Yes, I understand, and I understand that gas surface interactions are very complex sort of critters, but the fact that that's essential for a number of the derivations is important, because if you make certain assumptions regarding the gas surface interaction and then very rigorously derive a mathematical result, then the validity of the result is only as good as those assumptions. One other thing that I would point out is it can be shown for a molecular flow cavity where the mean free path is much longer than the dimensions of the cavity, that the gas in equilibrium is isotropic and homogeneous only if the outgoing angular flux distribution leaving the surface at all points is proportional to cosine theta. Now, you would expect that for a rough surface, for a randomizing type of surface, but for these newly engineered surfaces, the reduced dimensionality surfaces that are known to have many fundamentally anisotropic properties, optical properties, phonon, electrical properties, one might be surprised to expect that gas surface interactions, even for reduced dimensionality surfaces, have to be cosine. So That, to me, is a very fundamental issue associated with gases in real cavities, is resolving the cosine angular distribution issue, even for reduced dimensionality surfaces. So.
I can't answer your comment on the H theorem, but when you mentioned the surface problem, I would like to point out that the two-dimensional surface can be perfectly well described using Gibbs excess variables, and also in a non-equilibrium situation you can then define dynamic boundary conditions which you need, I agree with you completely, to match with the experiment.
Yes. Okay, thank you.
Okay. So another example is the heat conductions between two nanoparticles. Right? So in this case, new physics appeared in the sense that you calculate the heat conductivity between the two nanoparticles. It turns out that it depends on the distance, whereas for microscopic objects, it doesn't. So there are some properties that emerge at the nanoscales and are completely different to what's going on for microscopic systems.
Okay, my name is Zhou Zhang from Georgia Institute of Technology. And my question is for Professor David Zhou. And actually, I read your book and non-equilibrium and heat transfer. I like it very much. But then, basically, for the Fourier's law, and heat transfer thermodynamics are very much related. For the Fourier's law says that the heat flux is proportional to the temperature gradient. And the Fourier's law turned out to be follow the equilibrium thermodynamics, basic thermodynamics principle very well. And then there are discussions about the revision of the Fourier's law for the short time scale. Says that the temperature gradients not only depend on the heat flux, but also depend on the time derivative of the heat flux, which is gives to the equation of hyperbolic equation. And however, the hyperbolic equation violated the second law of thermodynamics. And so it doesn't work. So it looks like that your theory, and by redefining the non-equilibrium or entropy and others, that to kind of be consistent with the hyperbolic equation or the the Fourier's law. But however, and I do not know that whether you have any evidence or fundamental things. Normally that thermodynamics goes first, then using thermodynamics principle we derive the Fourier's law, and then this hyperbolic equation, of course, to me it has some problem. A lot of other people have shows the contradictory experimental results. But your theory seems consistent with that. Does it really prove anything or not?
In fact, in our theory, we must redefine the entropy in order that this hyperbolic thermal conduction becomes compatible with the second law. Therefore, without the degeneralization, the entropy production may become negative. And this is this expression for the entropy I have presented may be obtained from the kinetic theory of ideal gases, of quantum ideal gases, of radiation, of polymers, of different systems, and it has always this kind of form with this additional term, including the heat flux.
But there does not exist a foundation for the entropy definition that you have given.
Or this may be a phenomenon. This has several foundations. One is purely phenomenological, because then it gives an entropy, a positive entropy production. A second one is the physical interpretation of the additional extra term, which is the integral of the entropy production when we isolate the system, and then the system is far from equilibrium, it goes to equilibrium. There is a small entropy production which is incorporated there in this extra term. Or one may have a third derivation from f logarithm f as Boltzmann from microscopic grounds. Then therefore there are several different kinds of justification, from the purely phenomenological to this kind of projection of the non-equilibrium state on the local equilibrium surface or kinetic.
Maybe we can discuss more.
My name is Howard Butler. I'm a retired professor of mechanical engineering, and I would like to take issue very respectfully with something you just said, Mr. Hatsopoulos. You just stated that the second law of thermodynamics does not allow the entropy of the system to decrease. Did I hear you correctly?
That an isolated system, the entropy.
Okay. That's a very important condition that you must put on that statement, because an irreversible process can very easily lead to a reduction in the entropy. All you need to do is cool it.
I thought what George said is, let's talk some more. I thought you were going to disagree with that.
My name is Dusan Sekulic, and my question goes to both Adrian and Eric, inspired by a few things that I saw on your slides, which involves, in one case, social sciences, in another case, ecological systems. Most of us came to this field from from engineering or science, looking at physical systems. Somebody said that. So if you take the definition as it's given of a system, as it's given in this MIT school of thermodynamics, or nicely formulated in Giftopoulos' book and Beretta, there is nothing to find there that may exclude some other systems. However, we tend not to like to see those other systems like social sciences and other fields, an intrusion of those into thermodynamics or vice versa. So my question would be, could we properly define as systems to be prone to the thermodynamic analysis, the systems that are not necessarily physical systems, if we have proper set of analogies, and if we have defined the properties of those systems, and if we define the system correctly, well?
I'll go first if you. The three examples that I gave, the inanimate, which is the river basin flow architecture, the animate, which is really a river basin of animals flowing on the same landscape, and the so-called societal, which is our mass sweeping and scouring the same landscape, are not because of an analogy. It is because I defined each of these systems in the thermodynamic sense, if you wish, for this, to be brief. Each of those systems is a heat engine, okay, powering a vehicle, and the power output of that vehicle is eventually dissipated by rubbing against the environment. That's all there is. That is the model, and it works for all those things that I listed. And if you invoke the constructor law, then you discover, with your eyes closed, really, the configuration of that flow system. End of story. Therefore, and from the principle, the unification. Society and human taste and things like this are different things. They apply to the individual, but this is not what I've been discussing. It's been the flow of mass in the same way that in Dr. Schneider's presentation was the flow of water throughout nature. All right? All of it.
Yeah, just to add, we do agree about that. My position was rhetorical, because I recently noticed some very nice, very clever approaches, like Ingo Müller's, regarding social systems and his Hawks and Dawes theory. So I would like just to know whether we may be more comfortable with using the tools of thermodynamics in analyzing broader phenomena than physical systems.
That is an old field in which other, let's say, disciplines have tried to use our mathematical constructs, those of Gibbs, if you wish. No, that is not what we've been discussing. In fact, I have to give credit to Professor Giftopoulos for the little story with the evolution of the efficiencies of heat engines. Today was illustrated by Giampaolo Beretta. with his original graph. This is a story you told me almost 10 years ago at a NATO Advanced Study Institute, and it landed on my head at the right time because that's when the constructor law was taking shape. And it is the story, well, the evolution of the heat engines is not required or predicted by the second law. It's a different thing. It's a different phenomenon. It is evolutionary, like the unseen evolutionary patterns of Darwin. It is evolutionary, like the visible patterns of, say, river basin development right after that downpour. And it is eye-opening, the example that the configuration, or we heard pattern from one of the speakers, is itself a phenomenon. Earlier today, Bernard Guy spoke of needing principles of constructing the space, or a principle of the existence of the constructed or of the drawing. This is a subject that requires separate attention, serious discussion.
So, Eric, maybe you'd like to comment as well.
I'll just say one thing. My work in ecology aren't analogous to social systems the way you suggest. We parse these ecosystems very carefully with energy flow between organism and organism, and we can calculate all types of intricacies of the system. So it's interesting that we use the economic analysis as a means for parsing out our ecological data, information and energy flows that are used. So it's it's cross-disciplinary to say the least, but not totally analogous because I think we're dealing in hard science.
Good. Charlie. You know, we're running a little short on time, and I'd like to get the comments from the questions from the audience, and then if there's time, absolutely, it would be nice to have a comment from you.
Charles Bennett from IBM Research. I think there's some problem with both of the engines presented by Lindsay Gordon. In the one, the osmophoretic engine, it had a left side, which was the osmophoretic apparatus that generates a fluctuating motion of the piston rod, and then a right side that was rectifying those fluctuations in order to lift a weight. There's nothing wrong, in my opinion, with the left side. You can get fluctuations like that, no problem. The right side has a problem which was analyzed by Feynman in his Ratchet and Paul story. And essentially, what you drew there was a somewhat more complicated version of a Ratchet and Paul. That is, a device that should take a fluctuating motion and convert it into a steady rotation. And what happens in that kind of device, as Feynman showed, is that if the temperature of the ratchet is lower than the temperature of the fluctuating element, in this case your osmophoretic engine, then it will run indeed as in the direction that you say. But in the course of doing that, the ratchet will warm up. And when the two come to the same temperature, there will be no net motion. And if the ratchet is warmer, it will work in the opposite direction from the direction, and it never manages to violate the second law. Similarly with your rotary, yes, yes.
Oops. Yes. No, you're quite mistaken in the sense that I haven't got a ratchet and pull on the right-hand side. The ratchet and pull comes in with the solvent, the solute, moving through.
I'm not saying you have a ratchet and pull. You have another device that, like a ratchet and pull, aims to impose a directionality on the output from a fluctuating input. And I believe your right-hand side of your device is susceptible to the same analysis that Feynman did of his ratchet and pull.
Right. So the right-hand side of the device was the converter.
Yes.
Right? Converter, it jiggles away in Brownian motion. It moves as it wishes under thermal disturbance. But there's no ratchet and pawl there. The ratchet and pawl is in the left-hand device. You see, when the solute goes through...
The left hand I have no problem with. I believe it works as you say.
At all.
Yeah, the problem is only in the rectification on the right-hand side.
I don't have any pawl or ratchet on the right-hand side.
But you have something that is supposed to convert a fluctuating motion into a steady motion in one direction in order to lift the weight.
No, not steady. Fluctuating.
Fluctuating, but more one direction than another.
Well, why not?
Because, as Feynman showed, it doesn't work.
No.
Yes.
Okay,
Right.
well, but please, the other question from the other device then.
The other one, similarly, there are two elements. It's a little bit more subtle. There are the molecules colliding with this centrifugal pump.
Yes.
Coming in through the more centrally located aperture.
Yes.
And then there are the rotor itself. And if the molecules are hotter than the rotor, hotter, then both the rotor and the molecules will have Brownian motion. If the molecules are cooler than the rotor, it will pump in the direction that you say. That is, it will fling the molecules out like a rotary pump.
Yes.
If the molecules are hotter than the rotor, it'll work in the reverse direction. Hot molecules will come in, scatter off the come in on the outside, scatter off the rotor, and get pumped out the bottom. So I think both of these devices are microscopically reversible at the finest level and cannot be used to produce useful work from isothermal fluctuations.
Just one point about that. These molecules that are going through these are going from site to site. They don't have any momentum as they enter the chambers or the pores, right? They come in onto sites and jump from site to site. They don't have any individual momentum like a gas molecule going in and driving anything. So here again, you're wrong.
If they have some finite temperature, they have a momentum. They go
They do.
Yes,
They've got Brownian.
Yeah, the Brownian momentum. That's what I'm talking about. Yes.
Right. So
okay, this is enough for now. We can settle it after. Yeah.
You can punish him by not investing in his company, Charlie. Please.
I'm Noam Lior from the University of Pennsylvania. Actually, I had a similar question to Dr. Lindsay, and Gordon. I think the best way to prove what you're doing is do an experiment because all these speculations are not too fruitful. But my main point is more to Eric Schneider. And perhaps I misinterpreted your strong statement at the end that we are not going from order to chaos, but the reverse. One operational interpretation of entropy that also easily interprets why we can't get so much work is that it takes much less work to make a mess or a chaos than to make order. So perhaps natural systems move in the way that you are saying, that they're decreasing, they're doing some kind of optimization, as also Adrian says. But anthropogenic effects do increase the chaos. What we do is increasing the chaos, and they are slowly overwhelming what nature is trying to correct. And also, the last brief comment, there's some kind of implicit assumption that nature is ideal and is a highly efficient system, and it's not. Okay, a lot of processes, including photosynthesis, for instance, are very inefficient, in fact. So,
very inefficient.
Should I?
No, you would like to respond to that?
No, I'll talk to you later.
Yeah, well,
I was at a good team.
Yeah, that's a good one. The collection of energy from photons is extremely efficient. It's like 95 or 96% efficient. But the actual transfer of that energy into usable energy in the tree or biomass is very inefficient. Did you wish to also address, to defend yourself further, Lindsay?
I didn't think there was any defense to be made.
Okay, good.
There were comments, but there was no question.
Yeah, the question is, why didn't you do an experiment?
I'll answer that.
Do you know, Yes, let me say, I'm a Cambridge scholar, but I wasn't Keenanized, I'm afraid. And I've been with this work for 30 years, and I've been waiting for nanotechnology, because that is where it's going to take place. Now, I can only say that the remarks that you make have been made many times, and they're not, I'm sorry to have to take them, really. In my publications, much has been the worse without having had any critic over those 30 years, even though I've tried to show how Feynman was incorrect in the way he went about his Ratchet and Paul, how Szilard had not been so general in his work. It's just a very specific example of a very poor machine. And I don't know what more to say. I'm pleased that Professor Bennett was able to make his questions, and I'd like to see some written question to which I could answer to. Thank you. That's all.
Good. One last question, and then it's going to be time to adjourn.
I just want to ask this Drudjak now for this community, why is not exergy analysis more widely used in applications, especially stuff like electronics cooling? I know Eric mentioned it. I thought maybe Adrian, you might want to start since...
Well, on the use, maybe you should pose that question to the panel tomorrow, which is about teaching and the like. I don't think there's any reason for avoiding that method, as there's no reason to avoid the availability and other good lessons from very basic thermodynamics based on minimum words. So that's what I would say. Do you have 1 minute or two? I would like to respond to Professor Lior.
Why don't we have Sinye respond to this as well?
Thank you. No, I think that's a very appropriate perspective that you put on this panel. In my view, all the reason for working with the entropy production is to be able to understand better where exactly is the loss, the lost exergy or the entropy production, if you want it, so that we eventually can minimize it. And that's what it's going to be about tomorrow, maybe. But
I will just say that exergy analysis seems to be devoid in policy making in many places in government today. And I would think all of us that have some knowledge of this should put our foot in the wheel and try to encourage policymakers to do thorough analysis before they spend billions of dollars on a policy direction.
Hear, hear. Okay. We've now reached the end of our allotted time. I'm sure this has engendered lots of discussion. I urge you to take it outside and duke it out there. Or even better, as George wants us to do, the original meaning of symposium means drinking together. So have a glass of wine together this evening, and then I'm sure that tongues will be loosened and thoughts will flow. Cheers. Cheers, yes.